So in today's session, we are going to see Gauss's theorem and applications. I'll give you the theory part first, then we'll go to the numericals, equations and numericals. All right. So before starting off, let me ask you something. What is meant by electric flux? What is meant by electric flux? See this? I have an area here. This is an area. All right. On the area, we consider a small area of cross-section area like this. Okay. So we have taken a large sheet over which a small area is considered. And the area vector is drawn how? Area vector is always drawn perpendicular to the surface. Perpendicular to the surface. Okay. All right. So that is how you draw the area vector. And this is the direction of electric field. Just imagine electric field is penetrating in this direction. Okay. So see this? We have a large surface area. This is how, look at my palm here. This is how the surface is held. Not like this. Not in the plane of the board. The surface is held perpendicular to the plane of the board. Perpendicular like this. Perpendicular to the plane of the board. And on the surface, we have taken a small area. Small area is ds. Small area is usually written as ds. So ds vector, how do you draw area vector? Area vector is always perpendicular to the surface. Okay. Area vector, if this is the area, if this is the area, this is area vector. And if this one is area, you have to draw area vector this way. So area vector is always perpendicular to the surface under consideration. All right. So this is ds. I can split this electric field into two components. What are they? This is E sine theta and this is E cos theta. There is a normal component E cos theta. So there are two components over here. First one is E sine theta, second is E cos theta. And what is flux? This is the first probable question here. What is flux? A small flux is given by the product of normal component and area vector. Normal component and area vector. That is the first question. It's a previous question. Electric field is the product of what and what? Normal component, not tangential component. It is the product of normal component and area vector. This is question number 1. All right. It's a previous question, objective question. Okay. All right. Normal component of area vector and normal component of electric field and area vector. Or I can say it is E cos theta into ds. That way it becomes what? This looks like AB cos theta. AB cos theta is A dot B. So electric field is E dot ds. This is small flux. So what if the total flux is to be calculated? Total flux is given by integral E dot ds. So this is the first equation we have. All right. Or for numericals, we can directly use this equation. Phi is equal to E dot A. You won't have to use integral. You won't be having numericals with integrable functions. Understood? Electric field will be a constant. So don't worry about it. E dot A can be used. E dot area can be used for solving numericals. I'll do the numerical now. I'll come to that. So that is flux. So this is actually what? Flux is given by, flux's actual equation is E dot A. I repeat one more time. I repeat one more time. Remove it. I repeat one more time. Here we have a surface here, large surface. Large surface is usually written as S. Over the large surface, we have taken a small surface area. Small surface areas are usually called ds. Differential amount of surface area. All right. And then what? I told you there is a line, electric field line going in this direction. Actually, there are many of them going in this direction, but I've taken only one of them. Okay. And then what? That one is split up into two. One is E cos theta, E sine theta, tangential component. The other one is E cos theta. Look at this. This is the surface. This is area vector. This is the field direction. And electric field is split up into two. E sine theta, E cos theta and E sine theta. E cos theta is called normal component and E sine theta is called tangential component. Okay. And how is it defined? I told you flux is defined as the product of normal component of area, electric field and area vector. Never ever forget this. Normal component, never tangential component. There are reasons for it. Normal component of electric field and area vector. So E cos theta into ds. That is E dot ds, or flux is given by integral E ds, E dot ds. What does it actually mean? I told you there are many lines like this, right? Every line can be split up into two. Every line can be split up into two. And the normal components are being added up. That is what you do here. All right. Mathematically, this is how you do it. Okay. So actually it is what? If you have a surface and if you got a number of lines, you split them into two components, all of them like this, and add all the perpendicular components together. Understood? That is the name of flux. Understood? Understood? So there are so many field lines penetrating at an angle. and you resolve everyone into two components, and normal components alone are added up. That is the meaning of flux. Understood? You may have an assertion reason question there. Flux is this assertion. Flux is the sum of all the normal components of electric field lines. That's true. Understood? All right. Anyway, phi is given by E dot area. Another probable question here is unit of flux, Newton per coulomb. Area is Newton per coulomb into meter square. All right. Newton per coulomb into meter square. But electric field has another unit. Do you remember? Volt per meter is another unit. Volt per meter is another unit into meter square. So meter and meter are cut. So you get what? Voltmeter. So which of the following is the unit for volt? Which of the following has the unit voltmeter? They'll give you 4 values. Understood? One of them will be flux. Understood? That's a previous question. Okay, so we have seen how many questions here? One probable question. I told you flux is the product of what and what? Normal component and area vector. That is one question. Second one, a numerical from here. I'll do it now. Third one, flux is the sum of all the field lines. Assertion reason question there. All the field lines, normal components are added, not tangential. Understood? They might give an assertion reason like this. It's the sum of all tangential components. Is that correct? No. Understood? See, flux is what? I told you all the normal components have to be added. If they say tangential components, that's wrong. Understood? That statement will be wrong. Okay. And then the fourth numerical is, question is Newton per coulomb meter square or voltmeter. These are units of flux. So they might ask you, voltmeter is the unit of what? Voltmeter is the unit of electric flux. And I'll tell you the only numerical that has ever been asked on this part. Write this down. You can write. This is a previous question. Electric field is given by, previous question. We have done this in class. I plus 2j plus 3k. This is one numerical. I plus 2j plus 3k Newton per coulomb. This is one numerical that has been asked from this part. Okay. Electric field. Okay. And then area. They say area is 7 meters square. 7 meters square. I'm giving you the exact same question. 7 meters square in the XY plane. In XY plane. Area is in which plane? XY plane. 7 meters square in XY plane. All right. Find flux. Okay. Read the question here. This is a question, previous numerical. Electric field is given by I plus 2j plus 3k Newton per coulomb, and area is 7 meters square. 7 meters square in which plane? 7 meters square in which plane? 7 meters square in XY plane. XY plane means what? XY plane means I have to write it as area vector first. So 7k cap. Why k cap? It is in XY plane. Area vector has to be perpendicular to it, right? Oh, tell me what? This is XY plane. XY plane. This is the area. All right. This is x-axis. This is y-axis. And the plane of the body is XY plane. Where is area vector? Area vector is perpendicular to it. That is actually z-axis, right? Z-axis means k cap. Correct. So that is why I put k cap here. All right. So I'll repeat one time. Look at this. Electric field is given I plus 2j plus 3k Newton per coulomb. Area is given 7 meters square, and I have to make it 7k cap. 7k cap. Why 7k cap? Area is given in which plane? XY plane. See this? XY plane means area vector is perpendicular to it. It's z-axis. So I have to put k cap. Now I can find phi. What is the equation? I told you phi can be written as E dot A. This is what I wrote. For numerical, this is sufficient. E dot A. You know how to take dot product, right? How do you take dot product? I components are to be multiplied. I component here 1i, correct? I component here 0i plus j component here 2j, j component here 0j, k component here 3k, k component here 7. So answer is 21 Newton per coulomb into meter square. That will be the flux. This is a previous question. Okay. You know, I components are multiplied. What are I components? I told you I components are, look at this. This is I component, 1i, no I here. Here 2j, no j here. But 3k, 7k. 3 into 7, 21. Different plane, you know, you'll have, if it is in XZ plane, you have to take y, j cap for it. If it is in XZ plane, if it is in XZ plane, tell me, XZ plane, who is missing here? Y. Y means which x-axis is I cap, y-axis is j cap, z-axis is k cap. It is in which plane now? XZ plane. XZ plane means the perpendicular one is y. Y is j cap. So I have to put j cap. Negative is not to be negative, magnitude alone is sufficient. Negative is what? If you take the inward area vector, it is negative k cap. I took outward as k plus k cap. So y also, y is negative j cap here. It's fine, no issues. It's up to you. The choice of coordinate system is yours. You can take xz means j cap. Xz means j cap. You can take anything as x. If you want, you can take this as y axis and this as z axis. Doesn't matter. Okay, it's up to you. Anything can be taken x. Anything can be taken y. Anything can be taken z. Understood? But usually the rightward one is x axis, and the upward one is y axis, and the outward one is z axis. Understood? This way, outward, out of the board, like this. Okay, did you understand this? All of you, please. Okay, so we have done the first part. That's all about area vector questions, flux direct questions. So let us go to Gauss's theorem now. What is Gauss's theorem? We have a charge here. The charge, this is a charge, and charge is enclosed within a surface. This surface is called Gaussian surface. So what is basically a Gaussian surface? A surface that encloses a charge is called Gaussian surface. It can be of any shape, like even this can be called a Gaussian surface. All right, irregular shape. But for convenience, at your level, you'll see only 3 types of Gaussian surfaces. Which are they? Number 1, a spherical Gaussian surface. Number 2, a cubical Gaussian surface. Number 3, a cylindrical Gaussian surface. So these are the Gaussian surfaces you have this time. I'll repeat one more time. What is a Gaussian surface? A Gaussian surface is a surface that encloses a charge. That means you have to put a charge inside. Okay, you have to put a charge inside. All right. And this is an imaginary surface. I told you it can be of any shape, but for convenience, for practical convenience, and for easiness, we will take what? Only 3 types of Gaussian surfaces. Which are they? Number 1 is a sphere. Number 2 is a cylinder. Number 3 is a cube. And there are many numericals based on these. I'll tell you. Anyway, according to Gauss's theorem, what does Gauss's theorem tell you? According to Gauss's theorem, if you have a charge here, see this? This is a charge. And if you draw a Gaussian surface around this, the flux coming out of Gaussian surface is given by 1 by epsilon 0 into charge enclosed. Charge enclosed. If there is a charge outside, that charge won't affect the flux inside, flux from inside. Understood? Flux charge enclosed alone has to be taken. So if I have one charge inside, I'll take that charge only. Outside charges are not to be counted. So this is what Gauss's theorem says. According to Gauss's theorem, the flux coming out of a Gaussian surface, flux means what? Flux means the lines of force. See the lines of force? The lines of force, all the lines of force. See this? That is called the flux. Okay. Here I can directly call it flux. Tell me why? All are normal components, right? Only normal components. Am I correct? See this, all are normal only, all are normal. So only normal components are there. So I can directly call it flux. So flux coming out of a Gaussian surface is 1 by epsilon 0 into charge enclosed. All right. If there is a medium, the equation changes to what? 1 by epsilon 0, epsilon r, q enclosed. This is equation for flux coming out of a surface. If there is a medium present, phi is equal to 1 by epsilon 0, epsilon r into q enclosed. All right. So this is Gauss's theorem. Now I'll do the numericals here. See this? So 1 by epsilon 0 into q. Flux is given by 1 by epsilon 0 into q. There is a very important question. Tell me what? I have a charge here. Q. This was asked in your school paper this time. And there is a surface here. Okay. What if I increase the radius of the sphere, or if I double the radius of the sphere? What will happen to flux? Nothing will happen to flux. Why? Because flux is given by 1 by epsilon 0 into q. Correct? Flux is given by 1 by epsilon 0 into q. All right. Does it include any radius term? No. So no matter what the radius is, right? See, for a small sphere, or even for a large sphere, or even a much bigger sphere, flux will be the same. Correct? Why? Flux is always given by 1 by epsilon 0 into charge enclosed. This is an important question, many times asked. Unit flux. Newton per coulomb into meter square. We wrote it already. Newton per coulomb into meter square or voltmeter. There are 2 units for it. Epsilon r value, that depends on the medium. For different media, epsilon r values will be, they'll give in the question. Okay. So phi is equal to, all right. So flux will be what? Flux will be 1 by epsilon. Yeah, you can take these together, but that doesn't matter much. Epsilon 0, epsilon r, whenever you see them together, you can call it epsilon, simply epsilon, permittivity. All right. Epsilon 0 is permittivity of free space. Epsilon r is relative permittivity. Relative permittivity is a value which will be given in the question. That's relevant for the given material. All right. That value will be, for water, it is 80. Okay. Water alone you have to learn by heart. Other values they will give you. Okay. Water epsilon r value, it's better if you can learn by heart. All right. Anyway, let's come back to the question. This is a very important question. You have to make a note of this. All right. See, if the size of the sphere is increased, flux is not going to change. That makes sense, doesn't it? Look at this. I draw the field line. I draw the field line here. See this? I draw the field line from the charge. Say I have drawn some lines here. See this? How many lines have been drawn? Tell me. The first sphere is penetrated by how many lines? 1, 2, 3, 4, 5, 6, 7, 8. Am I correct? Correct. All these 8 lines would penetrate the second surface also. 1, 2, 3, 4, 5, 6, 7, 8. Am I correct? So lines penetrated. Lines penetrating the first surface is same as lines penetrating the second surface, which in other words would mean what? Flux is the same. Correct. Even if I take a bigger sphere here, no, even bigger sphere, again, flux would be the same. So no matter what the radius is, flux will be the same. That is common sense, because flux is given by what? 1 by epsilon 0 into Q enclosed. Okay. As long as Q enclosed doesn't change, you know, Q enclosed doesn't change, flux also doesn't change. And there is an important question here, which is a BPS question. Look at this. You know, we have a charge here, Q, and there is a sphere. There is another sphere. You know, this is another charge Q. Find the ratio of fluxes through first sphere and second sphere. You know, first sphere, I'll take first sphere. Tell me, flux through the first sphere is what? 1 by epsilon naught into Q. Correct. For the first sphere, I take out only what? Q as the enclosed charge, right? Yes. Yes. That's right. Flux depends on epsilon r also. Now, in the second case, phi 2 will be what? Phi 2 will be 1 by epsilon 0 into, there are 2 charges here, right? Q and Q. Correct? Q and Q together, Q plus Q. The outer sphere encloses how many charges? Inner sphere encloses only one charge, while outer sphere, look at the outer sphere. It has how many charges inside? This Q and this Q. Correct? There are 2 charges, right? So 1 by epsilon 0 into 2Q. Now we can find the ratio 1 by epsilon 0 into 2Q. So phi 1 by phi 2 will be what? Phi 1 by phi 2 will be 1 by epsilon 0 gets cut. You know, Q gets cut. Answer is 1 by 2. The ratio of fluxes is 1 by 2. Is that understood? 1 by 2. All right. So we have few equations here. Applications of Gauss theorem. First one is a thin sheet of charge. Thin sheet. This is a thin sheet of charge. See this? A thin sheet of charge. A charge sheet, no? It is having positive charges all around. Positive charges all around. All right. Positive charges. And here the Gaussian surfaces. Here the Gaussian surface is a cylinder. That will extend to either side. All right. So we have a Gaussian surface. What is a Gaussian surface? I told you, Gaussian surface has to be enclosing the charge. It has to be symmetrical as well. Symmetrical. Look at the symmetric as well. See this? This is the thin sheet here, no? See the thin sheet? Thin sheet is held like this. All right. So the thin sheet has half the cylinder here, half the cylinder here. All right. Because whatever is there on the left side should be there on the right side as well. Okay. It has to be symmetric. For this one, just memorize this. There are only 3 systems. One is a sphere. Second one is a thin sheet. Third one is a line of charges. Only three Gaussian surfaces are to be learned. First one is a thin sheet. Thin sheet, what is, I have a thin sheet. Thin sheet means the paper of your notebook. All right. There are so many charges on it. And on this side, we have a cylinder. This side also we have a cylinder. Actually, this is not to be drawn since it is MCQ based question. There will come here. Okay, so this is not to be drawn since it is MCQ based examination, but you know, but there can be questions on this. What is the flux through this? They'll ask you what is the flux through this, or what is the flux through this surface, or what is the flux through the surface. All right, we have done all these things in class. What about the flux through that surface? You know, area vector is to the right, correct? Electric field is in which direction? Electric field is to the right. Can you tell me why? If I put a +1 coulomb there, this plus sheet will repel plus to the right. Am I correct? How do you check the direction of field strength? How do you check the direction of electric field? You put a +1 coulomb over there and see where it is moving. Understood? So this plus sheet is repelling plus to the right. Both are in the same direction. So you can write the phi there, flux there. Phi right. It is what? E, A, cos 0, cos 0, cos 0. I take E into A. I call area D, not ds. I call area A. This is E. Similarly, what about this one? Here the area vector is to the left. Electric field is also to the left. Why? If I put a +1 coulomb here, this plus will repel plus to the left, plus to the left. Okay. So here also phi left will be what? Phi left will be E, A, cos 0. That will be again EA. Here it is what? Here it is area vector is upward. Look at that. Area vector is upward. For that surface, it is perpendicular, right? And then electric field is in this direction. Electric field is in this direction. Why? If I put a +1 coulomb here, this plus will repel plus in this direction. Look at the angle there. The angle is 90 degrees. So flux 180 doesn't come here. 180 doesn't come here. Here flux is theta is 0. Here theta is 0. On the curved surface, theta is 90. Curved surface, theta. So you can write it here if you want. Phi flat surface on the right side. Flux is EA. Phi flat surface on the left side. Flat surface means this flat surface. No, that looks circular, right? Correct. That is circular area. On the right surface, that is again circular area. So phi flat left, it is also EA. While phi curved surface is what? Phi curved is 0 because there theta is 90. Even here, look at that. Area vector is perpendicular. Electric field is in this direction. Angle is 90. So flux will be 0. Which one? Ah, this is the curved surface. Cylinder curved surface. Curved surface. Theta will be 90. All right. So flux is 0. So in this case, this is what you have to learn. Electric field, you can calculate it as sigma by 2 epsilon 0. Put this in a box. Electric field is given by sigma by 2 epsilon 0. Sigma by 2 epsilon 0. For which you have to draw the graph also. This graph hasn't come yet, but I expect this time. E and R. It's a previous competitive examination question. E and R. Direct. No, graph doesn't have distance dependence, right? No dependence on distance. Do you see any R term in here? No. There is no R here, right? So this is distance independent. Electric field due to a thin sheet. Electric field due to a thin sheet. We have done electric field due to a thin sheet. It is sigma by 2 epsilon 0. Sigma by 2 epsilon 0. Sigma, you know what? Surface charge density. Surface charge density. Surface charge density. So total charge by total area. Total charge by total area. That is called surface charge density. Total charge divided by total area. Okay. Surface charge density. And this is electric field equation. E is equal to sigma of 2 epsilon 0. This is E is equal to sigma of 2 epsilon 0. Sigma will be what? Sigma is electric field, surface charge density. All right. No distance dependence. So sigma will be what? See, electric field will be a constant. See, this electric field is a constant here. All right. Yeah, I can say E proportional to R raised to 0. No distance on dependence. No. There can be a question. I'll tell you. Electric field at a distance R is E. So what is electric field at a distance 2R? That is also E. Understood? Do not take it as 2E. So I'll write out the question. Hope you finish this. Okay. You don't have time. So I'm just right. So you can write this question. Write a question. Electric field at a distance. At a distance R from a thin sheet C. Thin sheet is capillary. What is that at? What is that at 2R? E at R is equal to what? Sigma by 2 epsilon 0. E at 2R is also what? Sigma by 2 epsilon 0. Both are same. So E at R is equal to E at 2R. That's it. All right. I'm taking every single point. That's why. Okay. You have to go to every nook and corner of theory part. That's what. All right. Such a simple question, but even then. All right. Hope you're finished. Okay. There are a couple of more equations. We'll go to the numericals then. All right. So we have seen one system, thin sheet, electric field due to thin sheet. Now we have thick sheet is removed from the syllabus. But anyway, just write it down. Thick sheet. This is thick sheet, just in case they ask. Okay. Thick sheet means the notebook, your notebook itself. Okay. This is called a thick sheet. Like, you know, thick sheet has charges all over it. Just write this down. This is not there in syllabus anymore. But anyway, just write this down. Electric field due to a thick sheet. It is sigma by epsilon 0. Deleted. But anyway, just write this down. Sigma thin sheet, it is sigma by 2 epsilon 0. Thick sheet is double of it. Just know that thick sheet is a combination of two thin sheets. Sigma by 2 epsilon 0 plus sigma by 2 epsilon 0. All right. Okay. All right. This is thin sheet, thick sheet. And I'll tell you two more. All right. So we'll do some questions now. Write one question. No. So this is a thick sheet. No, thin sheet is single sheet of your notebook. Thick sheet is the notebook itself. Notebook itself. Okay. All right. So let us draw one question. Find the electric field. This is a previous question so many times asked. Find the electric field. Find the electric field in the three regions. In the three regions. Find the electric field in the three regions. Find the electric field in the three regions. There are three regions, no? There are two thin sheets kept side by side, okay? There are two thin sheets. I'll do a previous IDA equation as well here. You know, there are two thin sheets. Look at this. The sheets are held like this. This one. See this now? See this? This is one thin sheet, another thin sheet. Thin sheets. Thin sheet, okay? Side by side. All right. We have done this question in class. This question came in your paper, right? We have done this in class. There are three regions. That is when plus and minus. Don't learn by heart. You know, look at this. You put a +1. That is how you check. Okay, you put a +1. You put a +1. Everywhere you put a +1 and check. Because they might give you different values here. No? Understood? So never learn things by heart. So I'm going to do for first one. Tell me, this plus sheet is repelling plus to the left, right? This +1 coulomb. Why should I put +1 coulomb? Because the electric field is checked by putting a +1 coulomb and finding the force on it. Okay. So I'm putting a +1 coulomb here. This plus is repelled to the left. So again, this sheet is doing what? That sheet is also repelling to the left. Correct? Correct. So both the sheets are repelling this plus to the left. So tell me what is E in the region number 1? It is sigma 1 by 2 epsilon 0 plus sigma 2 by 2 epsilon 0. That will be what? Sigma 1 plus sigma 2 by 2 epsilon 0. 1 by 2 epsilon 0 into what is inside sigma 1 plus sigma 2. Okay. Similar way, never learn things by heart. Try to get the logic, then it's easy. What about this +1? This plus is repelled by this plus to the right. That sheet is repelling this to the left. See this plus now, not 0, because they are not equal. Sigma 1 and sigma 2 are not equal, no? If they are equal, they are field in the middle. So here they are in opposite directions, right? So E2, region number 2, I can take what? Region number 2, sigma 1 by 2 epsilon 0 minus. Why minus? One is to the right, the other is to the left. To the right is taken positive, to the left is taken negative, because they are vector quantities. All right. So tell me what? Sigma 1 by 2 epsilon 0 by sigma 2 by 2 epsilon 0. 1 by 2 epsilon 0 into sigma 1 minus sigma 2. All right. Okay. And what about third one? E region number 3. E region number 3. There, as you can see, this sheet is doing what? This sheet is repelling it to the right. This sheet is also repelling it to the right. Both are to the right. Correct. So there you can add them up. Add them up. Sigma 1 by 2 epsilon 0 plus sigma 2 by 2 epsilon 0. 1 by 2 epsilon 0 taken common. Sigma 1 plus sigma 2. Understood? Sign on positive. Sign on in region 1 should be Oh, sign in region number, both are to the left. I forgot to put negative. These are both negative, no? They are to the left. To the left is to be taken negative. I forgot to put, I'm sorry. Okay, to the left is negative, to the right is positive. In region number 1, both are to the left, no? Both are to be put negative. Thanks for that. All right. So there is a special case of this question. Hope you finish this question. Okay. Shall I write this? I'm asking all of you. Tell me, please. All right. So do the next question. Find the electric field. Previous question again. Find the electric field. Find the electric field in regions 1, 2, 3. Find the electric field in regions 1, 2, 3. Find the electric field in regions 1, 2, 3. Here it is plus sigma, the other is minus sigma. Full minus. This is full plus. So this is basically a capacitor. Okay, capacitor. Because first plate is full of positive. Just the other day we learned. Second plate is negative, no? So here if I put a +1 coulomb, tell me what happens to it. Plus is repelling plus to the right, left. Minus is attracting plus to the right. See, this +1 is doing what? See what both the sheets are doing. This plus sheet is repelling plus to the left. Minus sheet is attracting plus to the right. Similar way here, tell me what? This plus is repelling to the right. Minus is attracting to the right. Here it is what? Put a +1. Here it is what? Minus is attracting to the left. Plus is repelling to the right. So let us write in region number 1. Tell me both left and right, no? Sigma by 2 epsilon 0 minus sigma by 2 epsilon 0. Don't put minus again because that minus has already been, okay. Sigma by 2 epsilon 0 minus sigma by 2 epsilon. So answer is 0. Correct. In region number 1, see this? Both the plates are giving in 2 different directions, right? This plus sheet is repelling to the left. Minus sheet is attracting to the right. They are opposite to each other. They'll cancel out. What about middle portion? Region number 2. Region number 2. We have done twice or thrice in class. Tell me, here both are to the right. Why both to the right? Because if I put a plus, this plus repels plus to the right. Minus, even if I take the phone, you won't get it back. Minus, this plus will pull it to the right. So both are to the right. Both are to the right means what? Both are to be added. So this one is what? Sigma by 2 epsilon 0 plus sigma by 2 epsilon 0. That is 2 sigma by 2 epsilon 0. These are cut. Answer is sigma by epsilon 0. What about the right side? There they are in opposite directions. E3, region number 3. Sigma by 2 epsilon 0 to the right, and to the left, it is sigma by 2 epsilon 0. You may have a tendency to put a minus sign for sigma, but never do that. Minus sign is already factored. That is why it is attractive. Okay. Yeah, one more is coming. I'll tell you. So sigma minus 2, sigma by 2 epsilon 0 minus sigma by 2 epsilon 0. They are equal. Yeah, they are equal in the question. They are equal. Sigma and minus sigma are equal. Okay, it's a typical question. It's a capacitor. This is called a capacitor. All right. So answer is 0. There the answer is 0. And till last year, this was a question like 3-mark question. Prove that electric field outside the plates is 0 and in between the plates is sigma by epsilon 0. That was a prove that question. Okay. All right. So this is basically a capacitor. And the problem is you may be given a configuration like this also. See this now. See this now. I'll draw one configuration here. I have an x-axis. I have a y-axis. Sorry, this is z-axis. I'm taking z-axis, x-axis. I'm giving exactly the same question. And I draw a couple of sheets now. See this? This is one sheet. This is second sheet. This is third sheet. Okay. Draw the figure, draw the figure. The sheets are not held in vertical orientation. They are given in horizontal orientation. They may give it like this only. That is like this also. All right. This is like minus sigma. This is like plus 2 sigma. This is like plus sigma. It's a question. It's not a graph. This is one sheet. I'll tell you. Look at this. There are 3 sheets. No. Prove that question is not needed anymore. So this is one sheet. See this? See this? One sheet here, second sheet here, third sheet here. Where are they placed? I am placing them at z is equal to the previous IITJE question. Minus a, z is equal to plus a. This is the most complex question they can ask from this. Plus 3a. But if you got the concept, you can do this on your own. Z is equal to minus a, z is equal to plus a, z is equal to plus 3a. There are 3 sheets put over here. Okay. So how are the sheets kept? Sheets are kept in this direction. Look at that. In this orientation. Now this is sheet number 1, sheet number 2, sheet number 3. So let us put the signs on them. Signs. I need to find the field here at P. Question is to find the field at P. Question is to find electric field at P. That is the question. Electric field at P is what? All right. Now, irrespective of the question, you're going to find it very easy. I'll tell you. Tell me. I'm going to put the signs. This is what? Minus sigma. Minus sigma means it is full of negative. Minus sigma means it is full of negative, right? Minus sigma means what? The sheet has negative charges. That's it. Sheet has negative charges. This is plus 2 sigma. So sheet has positive charges. Positive charges. Draw this. Positive sigma, no? This sheet also has positive charges. Positive charges. Positive charges. Why positive? Why positive? Because it is plus sigma. See that again. I'll repeat. You know, this sheet is what? They have given that this sheet is negative. This sheet is positive. And that sheet is also positive. Correct. Why? This is minus sigma. This is plus 2 sigma. This is sigma. Now tell me, you can put the direction. I'm going to put a plus 1 coulomb here. Plus 1 coulomb and see where it is moving. Tell me, where is it moving? What is this plus doing to this plus? A repulsion. So that is repelling it downward. Downward. Am I correct? That field is downward. Correct. Similar way, this plus is doing what? That plus is repelling this plus in the upward direction. Correct. You know, this is plus 1 now. That plus 1 is repelled or attracted. That's my question. This sheet is repelling plus to the right, downward, no? And this plus is repelling plus in the upward direction, right? And this minus is doing what? Minus will attract plus, so that will be in the downward direction. So I have 3 fields now. I'm going to write one by one. Okay, I'm going to write one by one. What is electric field due to the first sheet? Electric field due to the first sheet is sigma by 2 epsilon 0 in the downward direction. Am I correct? Correct. Downward direction. Downward direction. So I'll write one more time. Sigma by 2 epsilon 0 into minus k cap. Why did I put minus k cap? Because upward direction is the z axis. So downward direction is what? Minus z axis, right? See, I've taken upward direction as what? Z axis, right? It is given in the question. Upward direction is given as plus z axis. So downward is what? Minus z. So here the direction is minus z. Am I correct? What is unit vector for minus z? Minus k cap. So I put minus k cap there. Okay. Similarly, tell me what? E2, region number 2, field due to thin second sheet. Second sheet, tell me 2 sigma by 2 epsilon 0. Why 2 sigma by 2 epsilon 0? There sigma itself is 2 sigma. Understood? Actually, equation is sigma by 2 epsilon 0, but sigma is what there? 2 sigma. So 2 sigma by 2 epsilon 0. It is in which direction? It is in upward direction. Upward direction means I have to put plus k cap, right? Correct. No, you have one more. E3. E3 will be equal to what? Electric field due to third sheet. Third sheet is minus sigma, no? What about that one, E3? That is downward, right? Sigma by 2 epsilon 0. Downward means minus k cap. Correct. Now I can find the net of these. E net is equal to what? E net is equal to, tell me, sigma by 2 epsilon 0. This is minus sigma by 2 epsilon 0 minus sigma by 2 epsilon 0 minus 2 sigma by 2 epsilon 0 plus 2 sigma by 2 epsilon 0. Answer will be 0. K cap? Negative. One second. So we have 3 questions. We have 3 sheets here. Why is it negative in the downward direction? You tell me what is the direction of this? What is the direction of this? What is the direction of S1? See, there are 3 thin sheets given. First thin sheet here, second thin sheet here, third thin sheet here. And these are having what? Minus sigma, plus 2 sigma, plus sigma. All right, they can give anything. And this is plus, so it is all positive. This is plus, so it is all positive. This is minus, it's all negative. And they can put charge anywhere they want. No, they have put the charge here. Instead, if they put the charge here, you can find it yourself. They're asking you to find the field there. Can you tell me what happens now? No, let us do that again. That will be different. I'll tell you. Let us see. Tell me what is the field due to? What is the field due to this? This thin sheet. Tell me. This thin sheet is repelling downward, right? This thin sheet is also repelling downward. This thin sheet is repelling upward. Am I correct? Am I correct? So see this positive sheet is repelling plus in the downward direction. Positive is repelling in the downward direction. This minus is repelling in the upward direction.
So all downwards.
Oh, all downwards. Sorry. So see this again. I'll just draw it one more time. Look at this. Right. So this is where I have to find. Write this question yourself. Once you've done this, it's going to be easy. This is +1. I'm going to put a +1. Tell me one by one. This plus sheet is doing what? Plus sheet is doing what? Plus sheet is repelling downward. All right. Minus sheet is doing what? Oh, this is also plus. Plus sheet is repelling downward. Minus sheet is doing what? Minus sheet is attracting downward. So all the fields are downward. All the fields are downward. So E1 is what? Sigma by 2 epsilon 0. Sigma by 2 epsilon 0. That is downward. Downward is minus K cap. E2 is what? E2 is sigma by 2 epsilon 0. That is also downward. So minus K cap. E3. Sorry. Minus 2 sigma by 2 epsilon 0. Third is also minus sigma by 2 epsilon 0 K cap. Minus sigma by 2 epsilon 0 K cap. So altogether, E net will be what? E net will be, tell me, sigma by 2 epsilon 0, 2 sigma, 1 sigma. 4 sigma by 2 epsilon 0 into K cap. That will be the final answer. Understood this now? So we have seen that part. I'll move to second application, third application very quickly. We'll go to the questions. All right. See, the second application is electric field due to a spherical shell. Electric field due to a spherical shell. You can calculate electric field due to a spherical shell using Gauss theorem, and E outside is 1 by 4 pi epsilon naught Q or KQ. So I can take it as KQ divided by R square. This is E outside. And E surface is KQ divided by capital letter R square. E inside is 0. Electric field inside is 0. This is called electrostatic shielding or electrostatic screening. It is safe to remain inside the car when lightning strikes. Electrostatic field lines cannot penetrate this cavity. All right, you will be safe inside. And this equation may be asked in terms of sigma also. So this is how it looks like now. Sigma by epsilon 0 into R square by R square. Here it is sigma by epsilon 0. Here it is 0 itself. You have to write this down. So this is electric field due to a spherical shell. There are 3 applications. First one was what? First one was thin sheet. Okay, thick sheet is not there in syllabus, but anyway, just in case they ask, thin sheet is sigma by 2 epsilon 0. Thick sheet is 2 sigma by 2 epsilon 0 or sigma by epsilon 0. This is thin spherical shell. Spherical shell means where are charges residing? Charges are all residing on the outer surface. No charge stays inside. No charge stays inside. Okay. Nothing stays inside. All the charges are on the outer surface. So E outside is KQ divided by R square. And in terms of sigma, surface charge density, it is sigma by epsilon 0 into R square by R square. And E surface is KQ divided by capital letter R square, or it is sigma over epsilon 0. E inside is 0. All right. And the graph is also very important. Graph is important. This is how you draw the graph. Electric field against distance. Yesterday we drew potential against distance. Do you remember? For the same configuration, we drew potential against distance like this, because potential inside is a constant. Potential inside is a constant, right? Yes. Potential inside is a constant. Potential inside is also on the surface. Potential inside is same as potential on the surface. This is for potential that we drew. This is electric field. That time somebody asked me how electric field graph is drawn. This is how you draw it. Look at that. Inside electric field is what? 0. Electric field inside is 0. Electric field outside is proportional to 1 by R square. Surface is capital letter R square. All right. That is all about thin shell. And the third one is, this is important. There can be numerical. This time also in DPS there was a question. All right. I did that question in class. Look at this. Electric field is given by lambda by 2 pi epsilon 0 R. Lambda by 2 pi epsilon 0 R for a line of charges. This is called linear charge distribution. Linear charge distribution for which Gaussian surface is this. Gaussian surface is this. That is how you draw the Gaussian surface. Okay. Right. For cylinder, Gaussian surface would be a cylinder. This is the distribution, linear charge distribution. Okay. It is an infinite linear charge distribution like this. It is coming from infinity, it is going to infinity. For this surface, what is flux? Can you tell me? Area vector is up, right? Area vector is up. Electric field is to the right. Tell me why. Try putting a +1 Coulomb there. Plus will repel plus to the right. Correct. That is how you check. Whenever you want to find the direction of electric field, put a +1 Coulomb and see the direction. Look at that. Theta is 90. So flux will be what? Flux on top would be what? Flux through the top surface would be 0. How about flux through the bottom surface? See this now. Area vector is straight down. Correct. Area vector is perpendicular. Yes. Electric field, if I put a +1 Coulomb, that is to the right. Angle is 90 degree. All right. There again, flux through the bottom. Flux through the bottom is also 0. So no flux passes through top surface. No flux passes through bottom surface. The entire flux passes through curved surface only. Curved surface, I can take an area. This is area vector ds. Electric field is to the right. Electric field is to the right. This is +1. I put a +1. Flux bottom is 0. Flux top is 0. Flux bottom is 0. Entire flux passes through the curved surface. Curved surface. Okay. So flux is what there? Phi is equal to integral E ds cos 0. Just write this. They won't ask you, but even then. Okay. EDS cos 0, because E and ds are in the same direction, no? E and ds are in the same direction. So that is, this is for linear charge distribution. I'll tell you one question, linear charge distribution. They'll give you E value. That's a reader question. We have done this in class 2 times, and that was asked in DPS this term. Electric field. Electric field will be given. Lambda is the question. R will be given. Lambda will be the question. But for solving, it is better to write this as 2 and this as 4. Why? 1/4 pi epsilon 0 can be written as 9 into 10 raised to 9. Understood? Even though the equation is E is equal to lambda by 2 pi epsilon 0 r. Even though equation is this, it is better to multiply numerator with the 2, denominator also with the 2. Why? Because 1/4 pi epsilon 0 has a replacement. That is called 9 into 10 raised to 9. 9 into 10 raised to 9. Okay. 9 into 10 raised to 9 epsilon into divided by r. So you can put the value and find out. Okay. The question I'll tell you, this is how they ask the question. They'll give you E value, they'll give you R value, they'll ask you to find lambda value. That's a reader question, chapter and exercise question, many times asked in boards also. I'll tell you 2 example questions here. All right, 2 important questions here. See this? Please don't talk. See this? Question number 1, mark it as very important. Question number 1, what is the proportionality of electric field with the distance? Electric field and distance, you know, electric field is drawn here. Distance is drawn here. This is how the graph looks like. Rectangular hyperbola. Why is that a rectangular hyperbola? Why is that a rectangular hyperbola? Because E and R are inversely proportional. E and R are inversely proportional to each other. Inversely proportional. Okay. E and R are inversely proportional to each other. This is question number 1. Question number 2 is a far advanced one, but anyway, just write this. I'll tell you. First one is this graph. E is proportional to R, rectangular hyperbola. Only the shape is important. E is inversely proportional to R. They'll ask you to draw which of the following is the correct graph for electric field density due to a line of charges, linear charge distribution. The graph itself, you know, they'll ask you the graph. They'll give you 4 different graphs and they'll ask you to choose the correct one. Understood? We drew 3 graphs already. For a thin sheet, the graph looked like this. And for a spherical shell, the graph was this. All right. And the third application, all the 3 applications, I drew the graph. First one is not given in reader, but it is important. Okay. Electric field, and I expect this time. Okay. Electric field and distance are independent of each other. So there what? There the graph is a horizontal straight line. This is for a thin shell. And this is for line of charges. And there is an advanced level question here. I'll tell you. You know, see this? I have a linear charge distribution. Linear charge distribution. And an electron revolves around it. Electron revolves around it. Okay. Find its kinetic energy. Electron revolves around it, find its kinetic energy. Draw the graph of kinetic energy against distance. So write the question, an electron revolves around a line of charges. An electron revolves around a line of charges. Draw kinetic energy against, it's actually an advanced level question, against distance, kinetic energy against distance. An electron revolves around a line of charges. An electron revolves around a line of charges. An electron revolves around a line of charges. Draw kinetic energy against distance. Draw the figure as well. An electron is revolving around a line of charges. No, it's circular path. It's a circular path. No, it is actually revolving in this plane.
No, they asked a graph.
The graph, no, graph I have to draw. I'll show you. Graph I'll show you. Have you done this? Okay, I'll tell you how to do this. Now see this. I have the equation for here the circular motion is there. No, it is revolving, right? Circular motion means what? Whenever circular motion is written, centripetal force has to be written. What is centripetal force? Centripetal force is actually electrostatic force. Electrostatic force is what? E into E, Q times E. I'll write, say electrostatic force. Who gives the centripetal force here? Centripetal force is to the center, right? Centripetal force is to the center, right? If there is a circular motion, there must be a centripetal force. That centripetal force is given by electric force, because this is plus and electron is minus. There is attraction. So I can write centripetal forces, electric forces QE. So I can write it mv square by r is equal to Q is E. What is electric field due to a line of charge? You wrote it now, lambda by 2 pi epsilon 0 r. Correct? Lambda by 2 pi epsilon 0 r. I can cut r and r here. What will I get? mv square. mv square is equal to E lambda by 2 pi epsilon naught. I need half mv square. Kinetic energy, no? So I should multiply right side also with half. So that becomes E lambda by 4 pi epsilon naught. Is there any r in it? No. So kinetic energy, I can say kinetic energy is independent of distance, which means the graph is going to look like this. Kinetic energy against distance. Understood? I repeat one more time. See, we have this question one more time. This is line of charges, electric field against distance. This graph is important. Electric field against distance. Second one, they are asking a particular question. It's an advanced level question. It was asked only once. Okay, we have a linear distribution of charges. This is Ke. Oh, sorry, kinetic energy. We have linear distribution of charges. We have a linear distribution of charges. All right, and there is an electron revolving around it. Whenever you see the word revolving in a question, you must think about centripetal force. All right. Centripetal force is mv square by r. And who gives centripetal force here? You know, electrostatic force. Why? This is plus, this is minus. They have electrostatic attraction. Electrostatic force is Q times E. Q is E here because it is an electron that we're taking. And electric field is lambda by 2 pi epsilon 0 r. Electric field due to line of charges is what? We learned it today morning. Sigma by lambda by 2 pi epsilon 0 r. And this is r and r getting cut. I get mv square is equal to E lambda by 2 pi epsilon 0. And if I multiply the left side with half, I should multiply right side also with half. So that makes it E lambda by 4 pi epsilon 0. Now this is kinetic energy. Kinetic energy is independent of distance. No r here, right? E lambda 4 pi epsilon 0. That's a constant. So this graph is of kinetic energy against distance. Kinetic energy is independent of distance. We are moving to the last type of questions here. This is very, very important. Okay, I'll go on till the end and I'll come back and explain again. Okay, so we'll do numericals only. 3, 4, 5 questions are there. Right. Question number 1. See this. I have a charge here. This is a repeated board examination question. What is the number of lines of force coming from a +1 coulomb? Number of lines of force. Answer is 1.13 into 10 power 11. Number of lines of force coming from a +1 coulomb. How do you find number of lines of force coming from a +1 coulomb? Take a +1 coulomb and put it inside a Gaussian surface. Okay. Okay. And the lines of force coming out will definitely pass the sphere. Correct. So I can write flux instead. Flux is equal to 1 by epsilon 0 into what is inside? 1. If they say 2 coulomb, it is 2. 3 coulomb, it is 3. You know, usually they ask the number of lines of force coming out of +1 coulomb or number of lines of force associated with +1 coulomb. All right. 1 by epsilon 0 into 1. You solve it yourself. You're going to get this value. 1.13 into 10 power 11. This is a standard question, frequently asked question. Newton per coulomb. Sorry? Epsilon 0 is 8.85 into 10 power minus 11. So 1.13 into 10 power Newton per coulomb into meter square. This is the flux associated with +1 coulomb, or number of lines coming out of +1 coulomb. Remember, these questions are very important questions. What I'm going to discuss now. All right. Number one, the number of flux lines coming out of +1 coulomb, or the number of field lines associated with +1 coulomb. It is what? All the lines are coming out. All the lines are coming out. I just put that +1 inside. Once I finish, you can ask me questions. Okay. +1 inside, and then I draw all the lines. I can apply Gauss theorem. Gauss theorem, phi is equal to 1 by epsilon 0 into q. So it is 1 by epsilon 0 value you can put into 1. When you solve it, you will get 1.13 into 10 power 11 Newton per coulomb. So you try this, you will get this for sure. Okay, next question is, what is the flux associated with a dipole? This is a very important question again. Question number 2. I'm numbering here. Okay, plus q and minus q. What is the flux linked with a dipole? Put it in a Gaussian sphere. Apply Gauss theorem. 1 by epsilon 0 into charge enclosed. What is charge enclosed? Plus q here plus minus q. Plus q plus minus q 0. That makes sense. Why? All the lines coming from plus are ending on minus. Nothing is coming out. Understood? So all the lines coming out from plus will end on negative. This is question number 2. Number of flux lines associated with a dipole. Or even 2 dipoles, that's the same answer. 3 dipoles, 4 dipoles, but even quadrupole. There is something called quadrupole with the 4 poles. Minus q, minus plus q, minus q, plus q. This is called a quadrupole. All right. That is not there in your syllabus. But anyway, whatever you put, you add the charges. That's it. Okay. It's a dipole. Minus q plus q would be 0. That is second type of question. Now, the third question, we have done this in class. See this now. I have a charge here many times, 3-4 times I have done in class. All right. There is a square below. This is a reader question. You have to find the flux through the surface. Do you remember this? You have to draw you have this question in the reader. We have done this in class. You have to find the flux through the surface. All right. How do we do this? You will complete a cube here for symmetry. For symmetry, you will complete a cube. All right. Like this. A cube can be completed. And the flux passes through how many surfaces here now? Think again, cube means there are how many surfaces? The room in which you're sitting now. Left wall, right wall, roof, floor, front wall, back wall. 6 surfaces, right? Yes. So total flux is what? Total flux, don't talk please. Total flux is 1 by epsilon 0 into cube, phi total. Okay. This flux passes through how many surfaces? 1, 2, 3, 4, 5, 6. There are 6 surfaces. So one surface gets how much? 5 surfaces. Q by epsilon 0 by 6, or Q by 6 epsilon naught. All right. This is a very important question. Mark it as very important. Reader question. Many times asked. I'll repeat. We have a surface here. This is surface. They'll give you the value of side. One side will be given in the question. That is to confuse you. Understood? Even the distance to the charge also will be given. That is also to mislead you. Understood? Never look at those things. It is the answer, is standard answer, say q by 6 epsilon 0. Because you put a charge right here, and then what? Right in the middle, and then what? How many possible phases are there for symmetry? Left, right, up, down, front, back. All right, 6 surfaces. So flux can go in all directions, which means what? Total flux is q by epsilon 0. So flux through one surface will be q by epsilon 0 by 6. That is q by 6 epsilon 0. That is the next one. Let me come to that. Q by 6 epsilon 0. This is flux through one surface. And then there are few more questions over here. I'll tell you. I'll tell you 3 types of questions. These are important advanced level questions. Look at this. We have done all these in class, but I'm doing it again. Look at this. I have a cube here. And I'm placing a charge at the corner. Right at this corner. Okay. This corner. Okay. I'm placing the charge at a corner. So what is the flux through one cube? What is the flux through one surface? This is important, very important. This is edge corner centered, edge centered is there, body centered is there. There can be 3 questions. Okay, 3 types of questions. First one, this is corner centered. You are placing what? You are placing the charge at the corner. So how many more cubes are to be drawn for symmetry? One cube here, and there are two more behind this, right? There are two more behind this. All right, and above this, there are four more to be drawn, right? Altogether, how many are to be drawn? 8 cubes. So that this charge is in the middle. Charge is at the center, right? If I need, this is the charge, no? Initially, when I started off, the charge was at one corner. The charge was at one corner. One corner, okay? All right. And flux is going in which direction? All directions. So for symmetry, flux is going in all directions. So I need symmetry. I need to consider a symmetry distribution so that this charge comes in the middle. How can I do that? So I have drawn cubes here, 4 cubes, no? But above this also, I have to draw 4 more cubes. Okay, 4 more cubes like this. All right, so that, this is in the middle. So altogether, how many cubes? 8 cubes are there, okay? So one's total flux is what? Phi total is Q by epsilon 0 always. Correct? So what is flux through one cube? Flux through cube is what? Q by epsilon 0 by 8. So answer is Q by 8 epsilon 0. Q by 8 epsilon 0. All right, flux through one surface is flux through one cube is Q by 8 epsilon 0. But remember, how many surfaces are exposed here? See this, I'll draw it. Look at this. Look at this. I'll just draw it here. Don't talk, please. Look at this. I have the cube here. How many surfaces are gone? Right here, I'll just shade the surface. See this now? Just see the shaded surface. This surface is shaded. All right. That surface shaded. And the top surface is shaded. And even the back surface is shaded. Because there is a cube on the right side. There is a cube behind this. There is a cube above this. Am I correct? See, there is a cube coming over here, right? Which means that side is gone. Similar way, back side is gone. Top surface is gone. How many surfaces are gone per cube? 3 surfaces. Only 3 are available, right? 3 are available per cube. So altogether, how many are available? 8 into 3, 24 are available. So this is one available surface, one available surface, one available surface. All right. So one cube has how many available surfaces? 3. So how many in total? 8 into 3, 24. So flux through one surface is what? Surface, if they ask, it is Q by 24 epsilon 0. I repeat, I'll do that one more time. See this? Sorry?
So what are the other 3 surfaces?
Other surfaces are exposed, no? There's another cube, no? Actually, the flux is passing through that surface there, outside. Understood? So that will be counted on the other side. Don't worry. So see this again. So if this is for what? First configuration is this. We have the cube here. We have the cube here. And you are placing the charge where? You are placing the charge at the corner. You are placing the charge at the corner. See this? And then how many cubes are to be considered? If you find it difficult, at least learn this by heart because it's so typical and so important. Okay. How many cubes are constructed? 8 cubes in total. So flux through one cube. There are 2 probable questions. Flux through one cube is what? Q by 8 epsilon 0. Total is Q by epsilon 0. So one cube will have how much? Q by 8 epsilon 0 because everyone shares equally. And how many surfaces are gone? See this. This surface is exposed. Oh, sorry. See this. This surface is closed because there is a cube on that side. The top surface is closed. There is a cube on that side. Even the back surface is closed. There is a cube on that side as well. Okay. So how many cubes are available? Surfaces are available. Front surface, left surface, bottom surface. 3. So altogether we have 24 available. 3 into 8 cubes are there. No. So flux through one surface will be what? Surface will be Q by 24 epsilon 0. This is for what? This is for corner centered. Now, I'm taking face centered now. No, edge centered. Say this, edge centered now. Tell me edge centered. I'm drawing the configuration now. Edge centered means right here, edge centered. Right, edge centered. See this? For edge centered, I need to have these many cubes. See this now. Right, I have a cube. Draw the figure, That is how you draw this. Right, 4 cubes are needed. 4 cubes are needed. 4 cubes are needed. All right, 4 cubes are needed. So that is in the middle now, right? Exactly at the center now, right? How many cubes are there? 4 cubes are there, right? So what is flux through one cube now? Flux through one cube now? Q by epsilon 0 by 4. So that will be Q by 4 epsilon 0. Total flux is Total flux is what? Q by epsilon 0. Flux through one cube is what now? Total flux is Q by epsilon 0. This comes out through how many cubes? 4 cubes. So 1 cube gets how much? Q by epsilon 0 by 4. That is Q by 4 epsilon 0. And tell me about flux through one surface. How many surfaces are gone? Look at this. Look at this. You know, this is my cube now. This is my cube now. All right. All right. So which all surfaces are gone? This surface is gone because there is a cube on the right side. And back surface is also gone. So how many are available? 2 are gone means 4 are available, right? 4 are available, right? 4, 4, 4, 4. Altogether 16. So flux through one surface will be what now? Surface will be Q by epsilon 0 by 16. That makes it Q by 16 epsilon 0. Okay. So I do that again. Look at this. You know, this is what? This is for adjacent. Right in the middle of one edge, you are placing a charge. How many cubes are needed? First case, I needed 8 cubes. Here, I'll need only 4 cubes. 2, 3, 4. 4 cubes. So flux through one cube will be what? Q by epsilon 0 by 4. That is Q by 4 epsilon 0. And how many surfaces are gone? This surface is gone. All right. The back surface is gone. Only 4 surfaces are available. Front, side, top, bottom. Okay. 4 per cube. 4 into 4, 16. Q by 16 epsilon 0. And then the last one. The last one is, you know, you are putting the charge exactly at the center of a face ended. See this. This is face ended. I'll need one more cube here. That's it. I'll need one more cube for symmetry so that it is in the middle. See this now. I'll need only one more cube. Understood? So what is a flux through one cube? All these 3 questions are very important. Okay. Flux through one cube is Q by epsilon 0 by 2 because 2 cubes are equally sharing. Correct. 2 cubes are sharing. So that's going to be what? Q by 2 epsilon 0. And how many surfaces are gone? 1 surface per cube. Correct. Only 1 surface is closed. Correct. So 1, 1, 2. Only 5, 5 are available. 10 are available. So flux through one surface will be what now? Q by epsilon 0 by 10. That is Q by 10 epsilon 0. See this now? How many surfaces are closed? Open? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Only 1 is closed. 5 are available. 5 plus 5 is 10. So Q by 10 epsilon 0. So all these 3 questions are important. Don't talk, please. All the 3 questions are important. If it is corner, charge is placed in the corner, 8 cubes are needed. So Q by 8 epsilon 0. Flux through surfaces Q by 20 for epsilon 0. If charge is placed at the center of an edge, 4 cubes are needed. So Q by 4 epsilon 0. If surface is taken, Q by 16 epsilon 0. If placed at the center of one face, 2 cubes are needed, Q by 2 epsilon 0, and surface are taken, Q by 10 epsilon 0. The last question, what if you are placing body centered? That means at the center of the body itself. It is Q by 6 epsilon 0. Q by epsilon 0 is the total flux. Through the cube, it is Q by epsilon 0. Through one surface, it is what? Flux goes through all surfaces equally. How many surfaces? How many surfaces? All surfaces are available, right? So flux through one, the previous question again. Flux through one surface will be what? Q by 6 epsilon 0. Understood? Q by 6 epsilon 0. Here comes an important question. Q by 6 epsilon 0. Understood? This was also there in pre-board, right? This is a previous question. We did this in class. What the question is, charge is placed at the center. What is the flux through the cube? We have done this in class. It is there in our worksheet. Okay. So flux through one cube. Flux through the cube is what? Flux through the cube is Q by epsilon 0. Only one cube, right? It's already symmetric. When you place it at the center, it is already symmetric distribution. Correct? So flux through surface is what? 1 to the right, 1 to the left, 1 in front of you, 1 behind you, 1 above you, 1 below you. Altogether 6 surfaces. So that will be Q by 6 epsilon 0. Did you understand? We have this question. This is a typical one, very important one. Draw the figure. Find the flux through. Find the flux through. Write the question. Draw the figure. Find the flux through the curved surface. 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 Draw the figure. Find the flux through the curved surface. It's a typical question. I'll tell you how to do this. Find the flux through the curved surface. Tell me, look at this, look at this. You know, what is flux through the surface here? Total flux. I can say total flux is 1 by epsilon 0 into 0. It is equal to 0. Can you tell me why? No charge is enclosed, right? See this, see this. Is there any charge enclosed inside? No, they haven't given anything, right? So charge enclosed is actually 0. I can say that the total charge enclosed is 0. And this phi total is equal to 0. But phi total is the sum of what? Phi flat plus phi curved. Am I correct? Phi flat, because flux can pass through how many surfaces here? The left flat surface and this curved surface. Am I correct? Correct. So if I take a hemisphere, this is a hemisphere. How many surfaces does the hemisphere have? The left flat surface, right? And the right hemispherical surface. Correct? So phi total can be written as phi flat plus phi curved is equal to 0. So phi curved is our question. Phi curved will be what then? I can take this to like minus phi flat, because phi curved can't be found out directly. So we are using an indirect method here. Okay. That is also same. That is mathematically written this way. Understood? So this is what? Minus phi flat. So minus phi flat is given by what? E A cos theta. That is equal to minus E into area. Area of flat surface is that of a circular area, right? It is a circular area. Am I correct? This surface is circular, right? So pi r square into cos of, I would say the angle is 180. Tell me why. Here the area vector is to the left, correct? And the electric field is to the right. What is the angle between them? 180. Cos 180, right? Cos 180 is minus 1. Minus or minus plus pi r square E will be the final answer. I repeat one more time. Here the question is what? Question is to find, we have a hemisphere. Hemisphere kept in an electric field. Hemisphere is kept in an electric field. Hemisphere is kept in an electric field. You got to find the flux through the curved surface. Flux through the curved surface cannot be found out directly. Why? Because the angle is different. Look at the angle here. The angle keeps changing. Understood? So you can't find it directly. So we use an indirect method here. How do we do that? We use a technique. So we find the total flux first. What is total flux? Total flux is 1 by epsilon 0 into Q enclosed. But Q enclosed is what? Inside no charge resides. So it is 0. So 1 by epsilon 0 into 0, that will be 0. What about phi total? Phi total passes through how many surfaces? See how many surfaces does it have? It has only two surfaces. One flat surface, second one is a curved hemispherical surface. So phi total is 0. That is phi flat plus phi curved is equal to 0. Phi curved will be minus of phi flat. That is minus of phi flat is what? Phi is Ea cos theta. E dot A. Ea cos theta. So E into area. Area of the shaded region is what? That is pi r square into cos of theta is what? Look at that. Electric field is to the right. Area vector is to the left. Area vector for the surface is to the left. Angle is 180. Cos 180 is minus 1. Minus or minus is plus pi r square E. Did you understand this? Please do not leave. I'll tell you. Now the only question that is left over is the cube question. This is very, 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 very important. All right. So many times asked. You know, left surface will be at, I've done this multiple times in class. You know, the left surface is at a distance of 0.1 and the right surface is where? Right surface, the edge is also 0.1, which means right surface is at 0.2. I'll do this question in a separate session, but anyway, I'll just give you the value. This is the equation in the textbook. Values, these are the values. Alpha x raised to half electric field in x direction. Electric field in y direction is 0. Electric field in z direction is also 0, which means electric field x is only where? In x direction. Electric field is in x direction. All right. All right. So you can find the flux on the left surface, flux on the right surface. Flux through the top surface is 0, flux through the bottom surface is 0, flux through the front surface 0, flux through the back surface 0, because there are all those cases will have theta equal to 90, theta equal to 90, so flux is 0. Understood? This is a very, very, very important question. Even with change in data, this question has been repeated. Okay. So flux, the changed question was this. And that question also I did in class. CXI cap, electric field. It's a reader question. I mean, board question. This is a reader question. This is a board question. Okay. CXI cap. This is much better and easier. But this one is a reader question. We have done that question class. That's a previous question as well. Okay. So electric field is in y direction is 0. Electric field in z direction is 0. Electric field in x direction is alpha x raised to half. Alpha x raised to half. Okay. So left surface flux you can calculate. Right surface flux you can calculate. Top surface flux is 0, bottom surface is 0, front surface is 0, back surface is 0. All right. So find out phi left. Okay. I'll do that in a separate session. Find out phi right. Then what? Phi left, phi right. Then find out phi net. That is the first question. First question. Phi left and phi right, then phi net. Second question was to find the charge. How do you find charge? You can apply Gauss' theorem. Cross multiply. Q is equal to phi net into epsilon 0. For this question, you will get the answer as 1.05, if I remember correctly, 1.05 Newton per Coulomb into meter square. That's a repeated question, board question. So we have discussed every point from Gauss' theorem and applications, all types of numericals, everything has been completed. Okay, everything has been completed. So make sure that you learn this right away. Spend at least 15 minutes now itself. You learn this properly. Okay, so we'll come back with another session. So we'll meet again. Stay home, stay safe. Bye-bye. Take care. Thank you. ഇവിടുത്തെ നമ്പറിൽ വാട്സ്ആപ്പ് ചെയ്താണ്. സ്പിയറുടെ ജലം ഞാൻ ക്ലോസ് ചെയ്തു.